Hello, everyone. In this module 6 and the next module, I will discuss three clustering methods: the k-means, mixture model, and model-based clustering. Simply, k-means clustering is used to partition an observation into k clusters in which each observation belongs to the cluster with the nearest mean. And mixture models are probabilistic models for representing the presence of subpopulations within an overall population. Lastly, the model-based clustering assumes that the data were generated by a model and tries to recover the original model from the data. I will discuss the k-means clustering method in this module, and in the next module, I will cover the mixture models and model-based clustering methods. So in the previous module, we learned that run the hierarchical clustering method. The k-means clustering, which belongs to prototype method, is a machine learning method that uses data prototypes. A data prototype is a data values that reflects other values in its class. For example, we use the centroid in a k-means clustering problem. As you can see here, we have three centroids for X and Y data pair. However, the location of each centroid can be quite different. So please remember that the prototypes don't have to be existing observations, and the K prototypes, for example, centroid, can be thought of as representing K clusters. And prototype method can be used for data reduction, similar to PCA. So please refer to chapters 14.9.9 in the elements of statistical learning for more detail regarding the data reduction. The prototypes, such as the number of centroids, clusters, and location, should best represent the data, right? And this is done by the optimization method. And best is, of course, determined by the application. For instance, for data compression, the choice of K and MK is based on the trade-off between fidelity and the storage size. And for clustering, the choice of prototypes can give us different insights into the data structure. So the main points are that each point should be represented by the prototype that best represents it. Second, the prototype should be determined so they best represent the points assigned to them. So let's look into how the k-means clustering method work. K-means algorithms is designed to make each point is represented by the prototypes that best represent it. As I mentioned earlier, in k-means, the k cluster centroids are the prototypes. First, the kth centroid represents the nk observation assigned to that cluster, like this. Second, a point is assigned to the centroid that is nearest. Let's check the k-mean clustering algorithm here. And you don't need to understand these steps now. I will explain it step by step later. First, make k initial centroids mk, and these serves as initial cluster assignments for the observations. Second, we assign each observation to the cluster whose centroid is closest, where closest is defined using Euclidean distance. Next, update a centroid according to the points assigned to them. And we iterate this step until the cluster assignments stop changing. These are the notation for the equation of the previous slides. Let's use the old faithful data. This data is the waiting time between geysers eruptions in Yellowstone National Park, USA. The waiting time between eruption is between 35 and 120 minutes. Here I scale the waiting and eruption data using standard scalar function sklearn, the Python package. Let's check the dim note here. this line block, we can load the CSV data from a web server and scale them here. And I also deleted the duplicated data points. So here I show you the progress of the k-means algorithm with two clusters, k equal 2. This first figure shows the randomly selected two centroids, and each observation is assigned to the nearest centroid. Assigning the red or blue depends on the Euclidean distance between these two initial centroids. And the second figure is once again performed leading to new cluster centroid. And these figures are after 3, 4, 5, and 6 iterations. And as you can see, after 4 or 5 iterations, the cluster assignments stop changing. This is when we stop the iteration. So in this code block here, I load the k-mean clustering algorithm from scratch. Please check this code block, and if you have time, you can also try writing the k-means clustering algorithm from scratch. It's not a hard task. So the Python sklearn, of course, has k-means clustering library. And please check this code line for how to use a k-means library. Here I put 300 max iteration, just for sure. And please be aware that the algorithm would stop if it converges, so it would not go to 300 iteration. There's one question now here is how many iterations are enough for the algorithm convergence. To check when to stop iteration, we can check the MSA score for each iteration. I will explain how to calculate the MSA score in the later slide. And with our old faithful data with 2 clusters, 4 iterations will be enough for the algorithm convergence. And another issue is setting the initial locations of the centroids. There are many other methods that do not require the initial location of centroids. However, for our example, the initialization can be problematic. For example, these two initialization scenarios can result in significantly different results. This means that k-means could only find a local solution. So it is very important to run with several initializations and use the initializations that gives the best performance. And there are some strategies to help. First, we can initialize with hierarchical clusterings, and second, we can sequentially choose prototypes that are farthest away from existing centroids. In the 2 previous slides, we learned how to determine the number of iterations using MSA. Now, our next question is how many centroids or prototypes we should use, and the answer is quite simple. We can just learn k-means for several values of k and examine the sum of square error. Some people also use SSA instead of MSA to achieve this task. The SSA value can be calculated with the equation here below. And one thing you should notice is that each step will always reduce the SSA. For example, if the number of clusters is equal to the number of observations, SSA will be 0. So you can check this code block to on how to calculate the SSA. So in the case of k-means clustering, how many clusters should we look for in the data? A different number of clusters can have a strong impact on result obtained. In practice, we try several different choices and look for the one with the most useful or interpretable solution. So there is no single right answer. I believe any solution that exposes some interesting aspects of the data should be considered. The figure on the left shows 2 k-mean clustering results from k with 4 and 5, and figure on the right shows the SSA value with respect to the number of clusters, the k. We call an elbow plot, and we can use this elbow plot to select the appropriate number of clusters. With our example data and based on this elbow plot, the appropriate number of clusters is about 2 or 3. We can also use one of many statistical type tests. Please also read Hamley and Elkan 2003 paper if you are interested. As we have seen, to perform k-mean clustering, we must decide how many clusters we expect in the data. The problem of selecting k is far from simple, actually. Thus, the alternative approach is to use the more flexible Gaussian mixture models and use AIC or BIC and other statistical measures to select k. We will learn this in the later slide. K-mean clustering can be a very useful tool for data analysis in an unsupervised setting. However, there are a number of issues that arise in performing k-means clustering. These are some issues. First, k-means tends to find balanced clusters. Thus, clusters are around the same size, and there is no mechanism to permit small or large clusters. Everything is based on SSE. The second, k-means tends to find spherical clusters. This is because we use Euclidean distance. Thus, clusters will be more spherical, which means a larger k is needed to fit. In addition, it is very important to scale the data to treat each variable equivalently using Euclidean distance. And we need to scale the data appropriately. For example, we need to standardize all the columns to have equal variance. In the next module, we will learn the Gaussian mixture models, and they can provide a natural way to handle input features that have different scales. This is the last slide for this model.